In this presentation, we are going to discuss our next network theorem, which is Thevenin's theorem. And as the name is suggesting, this theorem was given by Léon Charles Thevenin, who was a French engineer, and in 1883, he developed the Thevenin equivalent circuit. And before we move on to the equivalent circuit and the statement of the Thevenin's theorem, we will first understand why Thevenin's theorem is needed. It often happens that a particular element in a circuit is variable while the other elements are fixed. Each time the variable element is changed, the entire circuit has to be analyzed again. To avoid this problem, Thevenin's theorem provides a technique by which the fixed part of the circuit is replaced by an equivalent circuit. So it is very easy to understand that in a large complex network, there is one element which is variable while the other elements are fixed. And when this variable element is changed, the analysis has to be done again. Now to avoid this problem, we replace the fixed part of the circuit by the equivalent circuit known as the Thevenin's equivalent circuit. And this equivalent circuit is very simple, and therefore, when the variable part is changing, we do not have to perform the tedious calculations again. All these points will become crystal clear by the end of this lecture. Now we will move on to the statement of Thevenin's theorem. According to the statement, a linear bidirectional two-terminal network can be replaced by an equivalent network consisting of a voltage source VTH connected in series with a resistor RTH. So as I said earlier, Thevenin's theorem provides a technique by which we can replace the fixed part of the circuit by the equivalent circuit, and the equivalent circuit or network will have VTH connected in series with RTH. So you can think about the simplicity this theorem is providing. Now what is VTH and what is RTH? VTH, which is known as the Thevenin's voltage, is open circuit voltage at the terminals. We will understand how we can calculate VTH in the network. And RTH, which is known as the Thevenin's resistance, is the input or equivalent resistance at the terminals when the independent sources are turned off. And we will understand how to calculate VTH and RTH by taking one example. To summarize our discussion till this point, I have taken this particular arrangement in which we have a linear and bidirectional network which is having fixed elements, and from this network we are getting two terminals across which one load is connected, and this load is a variable load. And therefore, for the simplicity, it is good to have the Thevenin's equivalent circuit in place of this network. And we know what is Thevenin's equivalent circuit. It is VTH connected in series with RTH. So here we have replaced this particular network by VTH connected in series with RTH. Now the only problem is we don't know how to find out VTH and how to find out RTH. For this, I have taken one example in which we are required to find out the current flowing through this load resistor, which is variable in nature, when it is equal to 6 ohms and it is equal to 16 ohms. I want you to analyze the given circuit for some time, and then we will move on to the solution. I hope you are done. Now we will move on to the calculation of current flowing through RL when it is equal to 6 ohms and it is equal to 16 ohms. And to find out the current, we will first find out the Thevenin's equivalent circuit. And we know to find out Thevenin's equivalent circuit, we need VTH and we need RTH. So first, we will find out Thevenin's voltage VTH. And for this purpose, we will make one modification in our network, and the modification is we will remove the load resistance and we will open circuit the branch like this. And we are doing this because VTH is the open circuit voltage between these two terminals. And remember one thing, always take the polarity like this and keep the polarity like this in the equivalent circuit as well. Do not reverse the polarity in the equivalent circuit, keep it like this. Now we will find out VTH in this modified network. If we talk about the current flowing in this branch, then it will be 0. Why? Because this branch is open circuited. And if I assume the potential at this node equal to 0, then potential here will be VTH. No drop will be there across this resistor because current is 0. And in this there are no resistors, therefore no voltage drop will be there in this wire, and potential at this node will be equal to VTH. And therefore if we can find out the potential at this node, we can have VTH. And to find out potential at this node, we will use nodal analysis. This is our reference node and this is our principal node. And let's say the potential at principal node is equal to V sub x. And we assume the potential at principal node to be the largest potential in the network. Therefore, all the currents in the branches connected to this node will leave this node. Let's say this is our current I1, this is current I2, and this one here is current I3. Now from KCL, we will have I1 plus I2 plus I3 equal to 0. To find out I1, we need the potential at this node, which will be 32 volts. And I1, it will be equal to Vx minus 32 divided by 4. Then we have plus I2. I2, it will be equal to Vx minus 0 divided by 12. So we have Vx divided by 12. Then we have plus I3. I3 will flow like this. This means I3 is the current moving in this direction in this branch, and it is opposite to the direction of 2 amperes current flow. Therefore, we will have I3 equal to minus 2. Now doing some rearrangements here, we will have 3 times Vx minus 96 plus Vx equal to 24. In the next step, we will simplify this further. We will have 4 Vx equal to 120. Therefore, Vx is equal to 120 divided by 4, which is 30 volts. And in this way, we have obtained the Thevenin's voltage. VTH is equal to Vx. Therefore, Thevenin's voltage VTH is equal to 30 volts. Now we will move on to the calculation of Thevenin's equivalent resistance. And to calculate RTH, we will do some modifications in our network. And the modification number 1 is same modification we did in case of calculating VTH. We will open circuit the load resistance. And the modification number 2 is turning off all the independent sources. This is our first independent source. We will turn it off by replacing it with a short circuit like this. And this is our second independent source, and we will turn it off by replacing it with an open circuit. And then we will calculate the equivalent resistance between the two terminals when looked from the side, and this equivalent resistance is known as RTH, the Thevenin's equivalent resistance. And when you observe the modified network, you will find 4 ohms resistor and 12 ohms resistor, they are in parallel. So RTH, it will be equal to 4 parallel with 12, and their equivalent is then in series with 1 ohm resistor. So we will have plus 1. From here we will have RTh equal to 4 multiplied to 12 divided by 4 plus 12 plus 1. When you solve it, you will have RTh equal to 4 ohms. So in this way we have calculated the Thevenin's equivalent resistance, and we already calculated the Thevenin's voltage, and therefore now we can have the Thevenin's equivalent circuit. The circuit will have the Thevenin's voltage, which is equal to 30 volts, which is connected in series with the Thevenin's resistance, which is 4 ohms, and we will have them connected to our load resistance. So this circuit is our Thevenin's equivalent circuit, and with the help of this equivalent circuit we are required to find current flowing through RL when it is 6 ohms and 16 ohms. So first we will assume the current flowing through RL to be I sub L, and in case number 1, when RL is equal to 6 ohms, we will have IL equal to 30 volts divided by 4 plus RL, which is 6. So IL is equal to 30 divided by 4 plus 6. So we have 3 amperes. In case number 2, when RL is equal to 16 ohms, IL will be equal to 30 divided by 4 plus 16. 30 divided by 4 plus 16, this will give us 1.5 amperes. So you can notice that even after changing the value of one element, the calculations are pretty simple to do, and this is because we have Thevenin's equivalent circuit. So I hope you now understand what is Thevenin's theorem, and in the coming lectures we are going to solve more questions on Thevenin's theorem. So this is all for this lecture. See you in the next one.